Thank you for the introduction, Dr. Yuma Shankar. So welcome to the webinar, Digital Twin in Power Electronics. Allow me to tell you a few words about me, a little bit more than what Professor Yuma Shankar just said. I'm a professor here in the Federal University of Santa Catarina, Brazil. My research area is power electronics, especially in digital control, multi-level inverters, power quality, and very recently, I started working with digital twin in this power electronics application. As Professor Yuma Shankar said, I'm a senior member of IEEE. I'm also the author of a few books, the Power Electronics Converter and Systems, volumes 1 and 2. And I'm also a author of a chapter in the Power Electronics Handbook edited by Professor Rashid. So this is the agenda of my presentation. I will start with the definition of digital twin, and very soon we are going to realize that we're going to have a more realistic model of our system. Then the next topic is to discuss a little why do we need a more realistic model, because pretty much our offline models are really reliable. Let's discuss a little features of the digital twin technology. I will show you how to make the digital twin setup much more realistic. Let's discuss the interface board because this plays an important role in this technology. Let's discuss the challenges in the optimization algorithm that they are really necessary in digital twin. I'll show you some alternatives to the optimization algorithm. I will show you my digital twin setup, and I'd like to discuss with you a little bit how to test algorithm in real-time simulation that makes no hardware necessary. I'll show you a few examples found in the literature, and finally some conclusions. Can you hear me well there? Let me know if you have some problems in the audio. And just before starting also, the idea here is just to present you fundamental concepts. I don't have yet many results of this research here in my lab, but the idea is to bring this technology as an introduction and show you just a few results that I have already. Let's so start with the definition. Actually, the digital twin is just a virtual representation of a physical system that continually updates its parameters based on real time from the actual system. What we are going to have as digital twin is actually just a model running in a real-time simulation, but this model changes its parameters constantly in real time. It's important to say that the concept of a digital twin is not new. Since the 70s, 60s, they, especially United States, used a lot of this kind of technology in their spatial missions. They have some telemetry communication, but they use a virtual replica of the ships in order to predict new results and in order to give more special attention to the modifications that they would apply for the course of the spatial shifts. But with the advancement of artificial intelligence, machine learning, and other artificial neural networks like that, other techniques like that, the digital twin brought new attention again. But it's important to say that it's actually important to say that this technology is actually not new. But again, with the advancement of artificial intelligence, we are going to see now a lot of new applications. And the fundamental idea is to compare the output signal of the digital twin with its physical counterpart, run an optimization algorithm, update the model, and enhance the performance of the real system. In this picture here, you're going to understand this very well. Consider here a buck converter, the topology of a buck converter, and suppose that we are going to realize it in a hardware, in a physical setup. Then we have the physical buck. Okay. Let's say that we're going to use the same buck converter, but now we're going to simulate it in a real-time simulator. As a result, we have the simulated buck. So far, we have two parts, the physical buck and the simulated buck. They are completely independent so far. So we can define two environments here, two parts. We have the physical part, and you have the virtual part. Okay. Let's put here an interface board to communicate between these two parts. And later we're going to discuss with more details this interface board, but it is important to say now that it needs to be bidirectional in information. Okay, two parts, the physical part, the virtual part, completely independent. I'm using the same parameters, but let's see how this will work as a digital twin. So let's grab here from the physical buck voltage and current. And let's grab also the same variables from the simulated buck. Let's put these variables in the interface board, and let's run an optimization algorithm in which we're going to minimize the difference between the currents and also the difference between the voltage. As a result of the algorithm, I'm going to have new values for the capacitor, inductor, resistance of capacitors, RDS on, and let's use these values in the model. That's the concept of the digital twin. We are going to compare what you're going to have in simulation against what we have actually in the physical buck, and the difference will be minimized in order to have this much more realistic, much more accurately when you see the current. That's the idea of the digital twin technology. Notice that we're going to discuss later with this algorithm, but we can add more parameters here. But the idea here is to keep changing all these values until this current will be equal to this one. Let's see in this next slide with the same information, but with more details. The idea of the optimization algorithm is to minimize the difference of the currents. In the end, my intention is to have this current here from the model, from the simulated model, exactly equals to this one. Then we're going to have a more realistic model. The algorithm itself will change all the parameters I want that are included in the algorithm. And actually, in the end, the virtual part is almost identical to the physical part. As a result, we have a more realistic model. But you may already notice that actually there are a lot of non-modeled phenomena here, like capacitance of the MOSFET, parasitic inductances. Pretty much this current will suffer a little bit to be equal to this one, and we're going to see that we're going to establish our threshold to consider that we have equal currents. Let's discuss this in a moment. In this part yet, we could add more parameters to the model, like the MOSFET capacitances, parasitic inductances, and others. But of course, if we add more nonlinearities to this model, the optimization algorithm may suffer to find the optimal point. So the next topic is, why do we need a more realistic model? Because our offline models from Simulink, PSIM, LTSpice are really reliable, especially from SPICE, because they have hundreds of parameters inside the components. We can change temperature of the junction, we can change capacitances, internal capacitances. If you take a look in the parameters that it's allowed to us to change in LTSpice, you're going to see that they have really reliable models. So why do we need a more realistic model? Other thing that make this question really interesting is that our experimental results often closely match simulation results. We see we have models like in a paper, math. We design controllers based on that. They work. We design models. So the question here persists. Why do we need a more realistic model? And the answer is we can do much more things. We can better design our controller for the reliability purpose. We can study the life prediction of components. We can also make some fault diagnosis to our system. We can also improve our thermal management. That's the reason we need to have a more realistic model. With that, we can make these kind of things and much more that as we will discuss in a moment. Since we have a more realistic model, we have this final phrase here in this slide. The digital twin can take control actions, predict scenarios, optimize control, identify anomalies and dangerous conditions, and generate a wealth of information to enhance future design and predictive maintenance models. If you go back to the picture that I have just presented to you, this is our digital twin, right? So if you have a more realistic model here, which is really confidence to the physical system, we can add now here some other algorithm in order to make condition monitoring. We can also make some reliability studies. We can also make some prediction of failures. In case you identify something unusual, we can change the Dutch cycle, maybe the parameters of the controllers, maybe the control mode, and you're going to see that you're going to have a flux of information from the simulated part to the physical part. That's the reason we have a bidirectional interface board up here. But again, with a more realistic model, using now other algorithms like a probabilistic algorithm to detect some failures in these capacitors, we've identified that these spikes here are stressing the capacitors too much. Let's try to change the parameters of the controllers in order to soften this and maybe prolong its life cycle and other things. That's the idea of the digital twin technology, keeping the parameters changing all the time. With that, I have a more realistic model. With this more realistic model, I can run a lot of wealth information to my converter. And if necessary, I can change, if I'm allowed to, I can change how the physical part works in order to preserve reliability and other stuffs. Okay, let's continue here. Let's see some features of the digital twin. Let's start with the non-invasive maps. If you see in the previous picture, the current and voltage sensors used to control the buck are used in the digital twin. I need current and voltage from the buck converter, so I can use the same sensors that are being used to control it to transfer this information to my physical part, the virtual part. It means that in these non-invasive methods, I know I don't have to add sensors or modify the hardware. I'm just using the information of the sensors that already exist in the power structure. But I have also invasive methods. In this case, I need to add extra sensors, and then I'm going to estimate the parameters like the series resistance of capacitor, the series resistance of inductance, RDS on, and other parameters that may be interesting. We know that reliable components with this technology you can try to avoid or postpone its failure with a more realistic model. We know from the people from reliability that DC capacitors and power semiconductors are prone to failure, and they have models to the lifetime, so we can use it in our favor and try to modify the controller if we identify something that is causing a dangerous or a stressful situation to the capacitor. As a result, components can be replaced before a breakdown happens. Another interesting feature of the digital twin technology that we are going to discuss in the next slide is the electrical and thermal indicators. And we know also that conditioning monitoring is the most important method to solve reliability problems of converters. Let's see here. And also, as to conclude this slide, so, yes, please. No, I have moved. Let's see. Yes, it seems something happened here. Let's see. What do you see now? Yes, let's return here. Let's see. This one with this orange line here. Yes, just let me know because this slide is similar to the previous. This one, why do you need a more realistic model? Did you see? Okay, this one. So when I said that we have algorithm running here in real-time simulator and being transferred to the physical bug. So let's continue from here. Features. Yes, please let me know if changes. Yes, let's see. I will repeat this again. Just a moment. Sorry, here. Thank you for letting me know that. Just let me know if you are seeing new phrases appearing on the screen. Okay, so let's repeat this part again. Features of digital twin. We have non-invasive methods in which the current and voltage sensors used to control the bug are used in the digital twin. It means that we are not adding extra sensors or modifying. Sorry, what is happening here? We are not adding or modifying the hardware in order to have the virtual part. We are just using the information of the sensors that already exist in the physical setup and transmitting these information to the virtual part. It means that we have a non-invasive methods. But we also have, let's see, invasive methods. In this case, you need to add extra sensors, but it is much better to estimate parameters like the series resistance of capacitors, series resistance of inductance, RDS on, and other parameters. As I said, we know that DC capacitors and power semiconductors are the most unreliable components. Using the digital twin technology with a more realistic model, we can try to avoid or postpone its failure when with this our model. We know, as I said, from people from reliability of power electronics, these components are really prone to failure, are the first to failure, DC capacitors and power semiconductors. We know some probabilistic models when they will be damaged. If we notice in our digital twin that something is causing a dangerous situations to the capacitors, we can try to avoid changing the model of our parameters. And as a result, components can be replaced before a breakdown happens. We are going to see in the next slide some electrical and thermal indicators. And also that we know that conditioning monitoring is the most important method to solve the reliability problems of converters. And also, let's discuss a little that thermal management, because heat is the cause of the degradation. This slide here pretty much summarizes that. Let me know if you are seeing here health indicators. Great. So starting with electrical indicators, because in our more realistic model, since the current are equal to the physical bug, for instance, we can take the electrical indicators. And a good one is the internal resistance of components, like the on-state resistance of MOSFET, the series resistance of capacitors. They are good electrical indicators. They will tell us how old the component is. Other indicators are the on-state voltage of MOSFET, the threshold voltage, and also the Miller plateau of MOSFETs. We also have the ability to get some thermal indicators, like the junction and case temperature of components, temperature, sensitive electrical parameters like the thermal resistance, and other parameters like the peak gate current, Kelvin emitter voltage, and the switching time. And this is really important. We need to know beforehand these values from the manufacturers, because when the component is new, they have some initial values. With knowing that beforehand, for instance, let's say that you see on the data sheet of a new MOSFET that the on resistance has such a value, you can save this information in your virtual setup. And then after a few months or after a few years, you can keep checking how different is the on-state resistance. As much higher the value, it means that the component is getting older. That's the reason they are indicators. So by knowing this information when the components are new, even the capacitor value and other parameters, we can say after a few times measuring it again, if the component is getting older. And of course, when you say that a lifetime of a capacitor is, for instance, 5 years or maybe 1,000,000 of cycles, you can count that and you can replace the component when you consider it necessary. Okay, that's the features of the digital twin technology. We can also make the setup much more realistic because we have here the buck converter running with a microcontroller. And initially, all the setup is running in the real-time simulator. I mean, the power structure part and also the control part. But we can add an external microcontroller to the real-time simulator. Then we're going to have a much more realistic scenario because the same algorithm of the controller which is running the physical part will be running here in the virtual part. In this case, only the power structure runs here in the real-time simulator and the controller runs in this. Having that, we can use this scenario to test new algorithms in the DSP with safety, with less time, not reducing the life cycle. Because again, you have here a more realistic model. You're going to run a probabilistic model of failures for components. You can try first here in this environment. And if you see that the results are satisfactory, then you can transfer new parameters to the controller of the physical part. Consider here, for instance, a charging station of a batteries. If you want to make a new algorithm to charge faster the batteries, these new algorithms may be dangerous to the real situation. So let's test here first in this setup, and then we can have a reduction in the time, we can prolong lifetime, and then adding this microcontroller really makes everything more realistic. Okay, let's discuss a little about the interface board. As I said, it needs to be bidirectional because signals from the physical part is traveling to the virtual part, like the current and voltage information of the sensors. But we also have signals from the virtual parts to the physical part as new values for the duty cycle, new values for the KP, or even changing the control mode. That's the reason we need to have a bidirectional capability in this interface board. Of course, everything that is being transmitted from the virtual part to the physical part should be allowed to do that. If you want to change the duty cycle, of course, you need beforehand if this is actually allowed, if your application allows you to do this. But at least we need to have a bidirectional interface board. The interface board may embed the optimization algorithm. You can have some FPGAs there or even other microcontroller there in order to run the optimization algorithm. We can also embed the optimization algorithm in the virtual part, since the real-time simulators and also our microcontrollers have several cores. You can separate one core just to run the algorithm, another core to run the model. The interface board may present low communication delays, and this one I think is the most challenging in this digital twin setup, which is the synchronization. Because if you take a look at this picture here, we are going to compare the simulated current against the real current of our system. So they need to be synchronized. It means this valley here should be exactly synchronized to this in order to make a fair comparison and try to make the algorithm reaches convergence. So synchronism. If you are talking about two buck converters, it means that the PWM must be synchronized. The carriers must be synchronized. This is actually quite a challenge because you have two microcontrollers. You need to have the same carrier in one and another. And you have also some distance. And we also have some distance. And maybe have a communication delay, so the carriers must be really synchronized. considering now we have a high frequency PWMs, any 1 microsecond, half microsecond of delay may desynchronize these currents and the comparison would collapse. Let's talk about some challenges in the optimization algorithm. Why this is not so easy to get? Because first, it's a model with several parameters that you are changing. You have here several local minimal points. The algorithm may be trapped into a local optimal point. Several algorithms have the calibration stage that you need to do before everything is working. Also, the convergence of at an optimal global point has some challenges. You need first to establish a threshold to stop the algorithm, because maybe the current will be never identical to this one. There are non-model parameters in the virtual part, so our simulated current will never be like this one. So the algorithm will keep trying to reach this current. In order to make this to converge, we need to establish a threshold to stop the algorithm. In any point, you need to consider, okay, stop here the algorithm, because this is enough for our digital twin technology. Again, because there are several nonlinearities that are not modeled, and the optimization algorithm tries to make the current identical, a threshold will solve this problem. We have another really high challenge in this algorithm is that you have a coupling effect between the closed loop operation. This current here is open loop. It's a bug for open loop, which is kind of easy to make the algorithm to converge. But when you are in a closed loop situation, any modification in the parameters, the controller will try to compensate, will try to make this minimize, because we will consider it as a disturbance. Since you have two environments, the physical and the virtual, the controllers are also identical, and then any modification in the parameters, the controller understands as a disturbance and try to compensate. So the interactions between the closed loop controller and also the parameters variation is quite challenging. Another difficulty in the optimization algorithm is the coupling effects, because power converters have multi-physical nature. There are a lot of temperature-dependent values, like resistance. It may change against temperature. So this multi-physical nature is also a challenge when developing algorithm for this setup. Let's see, can you see my screen? And even at the optimal, what's happening? Yes, let's see if you see this, because he did, yes, let's see. Even the optimal global point, it may be representing the real values. Let's see, just a moment. Did you see now that I changed the slides to alternative? Let's stop here. Let's change again. You mean just, I don't know why it's from time to time this freezes. Let's change. Yes, now you can read the left part here, even the optimal. So let's move here. Yes, that's good. Just to wrap up this slide, another challenge in the optimization algorithm is that even at the optimal global point, it may be not representing the real values of the physical converter, because essentially our simulation is a math equation and it may have several solutions. So we are not sure if such a solution that the algorithm is outcoming is actually which represents the reality. So we need to, in this calibration stage, to define which we consider really real values. Again, it's a math equation. It may have a lot of solutions. Just one solution actually represents the reality. Some examples of the algorithm are the PSO, genetic algorithms, and artificial neural networks. I invite you later to take a look of this algorithm. Some alternatives to the optimization algorithms. We can add sensors going to the invasive methods. As a result, you're going to have extra cost. But for a few parameters, just like capacitance, inductance, series resistance of inductance, it may be an alternative. One may say that I'm not considering, for instance, RDS on. Neither the algorithm consider all the parameters. So it's quite expected that we add sensors and estimate the parameters individually. We are going to set apart few parameters, but the algorithm does the same. We also have a few challenges when we do that, because the inductance may have a current which is completely constant, which is difficult to separate the AC and DC parts of the current in order to estimate, for instance, the internal resistance. Of course, choosing between invasive and non-invasive depends on the project's highest priority and interest. Depends, of course, what you have as a highest priority to your design, if it is low cost or if it is accuracy. Even in this case, adding sensors, we need to have estimation algorithms, but they are more accurate than the previous one, because we are going to estimate the internal values of MOSFETs, capacitance, and resistance with much more accurately, because these algorithms, they are really confident. Using these invasive methods as an alternative to the optimization algorithm will also bring us more health indicators. Again, we need to know beforehand all the values from the manufacturers, from the data sheet when the components are new, by measuring, for instance, the RDS on. From time to time, I can compare the initial value with the new one and say that if the component is old or not. At the end, we're going to have a trade-off solution as any other application. Let me show you here the setup that I have here in my lab, which I started recently, this research. But here you can see the buck converter, you can see the inductor, you can see the capacitors. You can see here the interface board, just having two sensors, one current and one voltage. These sensors are being used here in this microcontroller, but you can see here some cables that the information are being transmitted to the interface board. And here I have my real-time simulator running the model. You can see here that I have identical microcontrollers. Again, it is much easier to synchronize the carriers of these microcontrollers because they have some registers that it can be transmitted to this one. And this value of the registers can be set as 0 to this PWM. In the end, we're going to have a synchronized PWMs. This is my setup. Again, I don't have yet something really new running here, but it's ready for students there to apply new algorithms and test different things. I'm going to add more sensors here and try to get some parameters with the second method, which is the invasive methods. Actually, this is what I'm going to show here in these parameters. In my lab there, I'm trying both optimization algorithm and also the parameter estimation. Because the state observers are classical, I can use them to obtain, for instance, the series resistance of capacitors. I also have some common filter-based differentiators, which is really fast and attractive for parameters variation, like you see here in this picture. In blue here is, for instance, a value polluted with noise of an inductance. If something changes, just normalize, right? And then we can see how are the responses of different filters, like an infinity response filter, affinity impulse response filter, and the Kalman filter. Here you can see that it tracks this variation much faster. That's the reason I'm using Kalman filter differentiators to get internal parameters of components. Now, testing the algorithm in real-time simulation with no hardware. If you, for instance, are interested in running a few algorithms, you can use, for instance, the Typhoon Hill Control Center software to do that. You can have here in the left a buck converter with fixed values, fixed inductance, fixed resistance. Everything here is fixed. In the right here, you can have the same buck converter, but with variable components like a variable inductance, variable resistance, a variable capacitor, and another variable resistance here. What you're going to do is to grab voltage and current from the fixed buck converter, put them in the algorithm. You are going to collect the same waveforms here, current and voltage, bring them to the algorithm, run the optimization algorithm, and supply the new values for inductance and resistance. In the end, you're going to see if your component, if your algorithm is actually converging to an optimal point. I have here equal Dutch cycles, but in a more advanced situation, I can also change this Dutch cycle from the buck here in the left, which represents the physical buck, just to keep this more for another interesting, like reducing the stress of these capacitors as an example. Okay, so this is just to show you actually how to test some algorithm without having the hardware. Actually, this is what I did, what I do before testing the hardware. I'll test some algorithms here, but again, I don't have yet a lot of algorithms, so wait for a few months for publications and other things. But I brought you here a few examples found in the literature. I won't give you details of everyone, but the idea here is just to show you that the digital twin technology are much more focused on thermal management of power converters. We know, as I said previously, the heat is the cause of degradation. That's so really interesting to have a digital twin setup for thermal management. If you see papers in the literature, most of them deals with health monitoring and thermal monitoring conditions, because we know if the thermal indicators that something is out of its range, that is something is degrading the components. We know that the temperature, that for instance, when you buy everything new, you build a buck converter with new components, then you put your converters to run at the nominal power, at the rated power. You measure the temperature of the case temperature, you measure everything you can. So as new, you have such a temperature at the rated power. If you measure the same variables again in 1 year or 2 years, if this temperature is quite higher, it means that something is not under of its nominal range. So it's good to have some health monitoring as a thermal management. And if you take the literature, you're going to see that most of the papers using digital twin technology nowadays are much more focused on the thermal indicators, much more than parameter estimation. But I give you here just an example, and you can see here what is the converter, what are the algorithms. Most of them are this one, the particle swarm optimization, which is the most classical one. You can see here some features if they are invasive or non-invasive. Here are the list of these references. I can share you later this presentation, so if you are interested, you can take a look. But you see here that they are quite new, 2025. You're going to see a lot of papers really recently published. And also, I'd like to show you here this call for paper. It is already almost published. The date here is quite old. It is not published yet, but I brought you this just to show you there is a special issue in this really important journal exclusively for digital twin driving high reliability power electronics system. It is not already available on the internet, even though the date here is already old, but we are waiting for these papers to check the most new and modern solutions on this topic. That's just to give you this, right? So thank you for everyone for watching this. I hope I brought to you here the idea of the digital twin technology. That was the purpose of the webinar, just to present you fundamental concepts. Again, I don't have yet many results to present you, but the idea was to bring this and have a nice talk, and now we can open to questions. And I invite you to take a look later in my books. This one was published last year by IET. They combined it, have 28 chapters with a lot of topics in power electronics. Okay, so thank you very much. If you have a question, you may ask in the chat. You may also write to me an email. I'll be so glad to answer all your questions. I hope you got the idea of the digital twin technology. And also, thank you very much, Dr. Mashankar, Professor Mustafa, for the invitation. It was my pleasure to present this webinar to the Prince Sultan University. Thank you. That's nice. Good. Thank you. Okay, you can type your question. You can open your microphone and say your question. Yes, no, it's open to any other domains. I have a lot of domains like thermal, electrical, mechanical, magnetic. You may find a lot of different domains to that. The thermal is the most preferable one because it's a good indicator. The temperature actually is a good indicator. Again, let's say that you buy a new MOSFET. You put this new MOSFET to work at full power. So it's new, you measure temperature. All right, let's say 80 degrees. Okay. Measure the same the MOSFET in the same condition again in 2 months. And then you see that the temperature is quite higher. It means that the component is actually getting old, it's obviously, but depending on how much this value left from the original one, you can have an idea how old is this component. So the temperature is good. I don't know if this was your question, but did I answer your question? Exchange what? Yes, yes, you can extend to any other variable that may be interested to you, and actually that may represent some wealth condition of your system. You can extend. Let's see here on YouTube if there is a question. Okay. We are going to launch certificates to your students. That's great. If you need my signature, just send to me. I'll try to sign. For me, it's okay. Okay, Dr. Umar Shankar, if you have more questions, you may write to me by email. Feel free to ask now. It's up to you. I, yes, yes, please go ahead. Yes, 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 sure. That's great. Thank you very much for all of you. So feel free to ask me questions by email. If you have questions, feel free to write to me. So see you. Have a nice rest of week. Have a nice weekend. See you around. Bye bye.